In this section, we are going to see about some proofs. Giving a proof for something is an important part in mathematics. So, here if you see our learning outcomes, after finishing this session, you should identify appropriate methods and applying them in the proof of mathematical statements. Here there are some proofs. First one, direct proof, proof by contradiction, proof by counterexample, proof by mathematical induction. First one, direct proofs. Here we should start with a given fact, and after that we are going to use logical reasonings to deduce other facts. Keep going until we reach our goal. Here we can see an example, that is, we are going to prove that if x and y are odd integers, then we should prove xy is odd. Solution for this one, say x and y are odd, then we can write the odd numbers in that format, that is, x is equal to 2m plus 1 and y is equal to 2n plus 1 because they are odd numbers where m and n are integers. Then we can multiply those two values, that is x and y, then we can get 2m plus 1 into 2n plus 1. If we multiply 2m and 2n, then we can get 4mn. In that way, we can get 2m, 2n plus 1. If you see the first three terms, we can take 2 as a common factor, then we can take 2 out, then we can get 2mn plus m plus n plus 1. If you see this pattern, it is in the form of 2 into some integer value plus 1. Then we can write it like that one, that is xy is equal to 2p plus 1, where p is an integer since m n and m and n are integers. So, if you see this pattern, this is the form of odd pattern. So, we can say xy is odd number. So, this is the proof for direct proof. The other method is known as proof by contradiction. Instead of starting with the given known facts, we start by assuming the opposite of fact of what we seek to prove. Use logical reasoning to deduce a sequence of facts, eventually arrive at some logical absurdity. Here we will see an example, that is, we are going to prove x not equal to 0 if x squared minus 8 is equal to 0. So, here we are going to prove x not equal to 0. So, it is the proof for contradiction, that is why we are going to assume x is equal to 0. Then we can substitute this 0 in the equation x squared minus 8 is equal to 0. Then we can get 0 squared minus 8 is equal to minus 8, which contradicts our fact, that is x squared minus 8 is equal to 0. Hence, we can come to the conclusion our assumption x is equal to 0 is false. Therefore, we can say x not equal to 0. This is another type of proving, that is proof by counterexample. To show that a statement of the form for all x p is false, it is equal to showing that there exists some value, it will make negation p true. That is, there is an element x which makes negation p true. We will see an example, that is, for all x p, that p is x squared minus x when x is a rational number. So, we are going to prove that is for all x, then x is false. By using the counter example, we are going to prove this one. Say when x is equal to half, we can get 1/4 greater than 1 upon 2, which is false. Because if you substitute half in our previous equation, that is x squared greater than x, then we can get 1 upon 4 greater than 1, no, then hence false, because half is greater than quarter. That is, there exists a value of which makes sense. So we can say there exists a value half that will make the statement for all x p false. There is another method, it is proof by mathematical induction. Principle of mathematical induction, let p of n be a statement that is either true or false for any positive integer n. Suppose we have p1 is true, that is when we are substituting the first value, it should be true. And we are going to assume p of r is true. We can show that p of r plus 1 is also true for all positive integers r. Then p of n is true for all n greater than equal to 1. Then what are we going to do is, first we are going to substitute the first value and we can show that is true. After that we are going to assume that p is true for the value r. Then we can show from that one, that is p of r plus 1 is also true. From those things we can come to the conclusion p of n is true for all n greater than equal to 1. See this example, here we have to prove that 1 plus 2 plus n up to n, that is summation of n is equal to n upon 2 into n plus 1 for any integers n greater than equal to 1. Let us see the solution. Say Pn is the summation of n which is equal to n upon 2 n plus 1. We should prove this one. So when n is equal to 1, p of 1 states 1 is equal to half into 1 plus 1, which is true because we know half into 1 plus 1 is going to be 1, then we can say p of 1 is true. Result is true for n is equal to 1, that is p of 1 is true. Then we are going to assume that the result is true for n is equal to r, that is assume that p of r is true. Then we can say summation of r integers is equal to r upon 2 into r plus 1 because we assume that p of r is true. Then we are going to add r plus 1 to both sides. Then we can get 1 plus 2 plus 3 up to r plus 1, that is summation of r plus 1 which is equal to r upon 2 into r plus 1 plus r plus 1 because we are adding r plus 1 to both sides. Then we can solve this equation, we can get r plus 1 upon 2 into r plus 2 because r plus 1 is a common factor, then we can take it out, then we can have r plus 1 by 2 into r plus 2. Then we can rearrange this equation into that format, that is r plus 1 by 2 into r plus 1 plus 1. If you compare this result with our previous result, that is n by 2 into n plus 1, then here also we have that format. Therefore, result is true for n is equal to r plus 1, that is p of r plus 1 is true. So, we have shown that when n is equal to 1 it is true, and after that we assumed that p of r is true. We show n is equal to r plus 1, that statement is true. Then we can come to the conclusion p of n is true for all n greater than equal to 1. That's all.
Recording start.
In this section we are going to see digital logic circuits. At the end of this lesson, you will be able to learn how to design various logic circuits. Digital systems are said to be constructed by gates. These AND, OR, NOT, NAND, NOR, XOR and XNOR gate. The basic operations are described below with the aid of truth table. Now we will see the AND gate. Here we have two inputs A and B. From the truth table, we can get the output of A and B. That is, when A is 0, B is equal to 0, then we can get AB 0. This way we can get the truth value. So, a dot is used to show AND, that is A and B. The AND gate is an electronic circuit that gives a high output 1 only if all its inputs are high. The next one is OR gate. Here also we are going to have two inputs and a plus is used to show N, that is A plus B, and the truth table is given here. The OR gate is an electronic circuit that gives a high output 1 if one or more of its inputs are high. This is a NOT gate. This is also shown as A dash or A with a bar over the top. Then there is a truth table here. The NOT gate is an electronic circuit that produces an inverted version of the input at its output. It is also known as an inverter. If the input variable is A, the inverted output is known as not A. This gate, the truth table is given here. This is a NOT AND gate which is equal to an AND gate followed by a NOT gate. The output of all NAND gates are high if any of the inputs are low. The symbol is an AND gate with a small circle on the output. The small circle represents the inversion. This is NOR gate. NOR gates are low if any of the inputs are high. The symbol is an OR gate with a small circle on the output. Here also the small circle represents inversion. This is XOR gate. The exclusive OR gate is a circuit which will give a high output if either but not both of its two inputs are high. An encircled plus sign is used to show the EOR operation. This is the exclusive NOR gate circuits does the opposite to the XOR gate. It will give a low output if either but not both of its two inputs are high. The symbol is an XOR gate with a small circle on the output. Here also the small circle represents inversion. By using these basic gates, we can multiple input gates. Here is an example. Here we are using two AND gates. For the first AND gate, we are giving A and B as an input and we can get A and B as an output, and we will send this A and B and C for the another AND gate, then we can get A and B and C. Simply we can represent this multiple input gate by a single AND gate. This is an example for the multiple input gates. So, by using these basic gates, you can implement several multiple input gates.